In this video we will look at linear recursion in a bit more depth. I will describe what I mean by linear recursion. We have mentioned earlier that when designing recursive programs, think about the problem in recursive terms. Do not think in terms of the stack that is used in execution. When it is actually executed, there will be a stack created and used for the execution, and the depth of recursion is a term which means the maximum size of the stack while you execute the program on a given input. The memory used by the programs includes the local memory of the function plus the depth of the stack. So, let us look at linear recursion in a bit more detail. By linear recursion I mean problems which can be solved by calling an instance of the subproblem, okay, exactly one instance of some subproblem. We will see more general kinds in later videos. Let us look at an example that we have seen before, which is reversing an array in place. So, we had to reverse an array A with n elements, and it is supposed to reverse the values contained in the first n indices of A, that is A0 is exchanged with an minus 1, A1 is exchanged with an minus 2, and so on. So, we have to do n upon 2 exchanges approximately. So, let us look at the problem recursively. We had earlier solved it using loops. Now, the basic idea of the recursive solution to in place reversal is the following. If n is 0 or 1, if the array is either empty or it contains exactly one element, then we do not need to do anything to reverse the array. Otherwise, it contains at least two elements. In this case, exchange A0 with an minus 1, that will be the first layer. Now, call the subproblem. We have to solve one more subproblem, which is reverse on an array which is from A1 through an minus 2. Notice that we had already solved the problem of swapping A0 and an minus 1. So, earlier we had seen a program which involved linear recursion which just went left to right. Okay. In the case of reversal of an array, it is still linear recursion in the sense that there is only one call to a subproblem, but the way in which you call the subproblem is slightly different. Let us see with an example. We will consider actually two examples, one for an even length array and another for an odd length array. Let us say that A is an even length array with 6 elements and we want to reverse it using the function reverse A6, and we have to do it in a recursive way. So, what you do is first swap A0 with A5, and now what is the subproblem left to be solved? We have to solve reverse of this intermediate array which starts from A1 and contains 4 elements. Okay. So, we have to reverse the array which starts from A plus 1, and there are 4 elements to be reversed. So, in one step, even though we have only a single call to a subproblem, we have actually reduced the size by 2. Okay. And now use reverse or rather swap A1 and A4, and now the subproblem that remains is to reverse this subarray, which is A plus 3, and you have 2 elements to reverse. Okay. So, you do this, and at this point you have a subarray which starts at A plus 3 and has 0 elements to reverse. At this point there is nothing left. Okay. Now, for an odd length array, let us take a very small array which contains 3 elements and we have to reverse it. What you do is you reverse, you swap B0 with B2. At this point you have a subproblem which has exactly one element, and you do not need to reverse that array is its own reverse. So, the problem just stops there. So, notice the difference between the even length array and the odd length array. In the case of an even length array, the step just before the last step involved an array of size 2, and you still had to reverse that array. In the case of an odd length array, the last step involves a single length array, which is its own reverse. So, you do not have to do anything. So, there are two base cases to worry about. One is where the subarray is of size 0 and another is where the subarray is of size 1. 0 corresponds to even length arrays and 1 corresponds to odd length arrays. Let us write this code now. Okay. So, we have reverse A containing n elements, and we have return type void, which means that this function is not going to return you a value, but it is going to do something. Okay. So, if n equal to 0 or n equal to 1 return, because in that case A is its own reverse. Otherwise, you swap the first element with the last element, that is this operation A and A plus n minus 1. So, notice that swap is a function that takes two pointers to int and exchanges them. Once you do that, you call the sub problem, which is reverse A plus 1 n minus 2. Notice that unlike the previous examples we have discussed, the sub problem reduces by 2 in size. Even though you have only a single call, the sub problem is not of size n minus 1, it is of size n minus 2. So, look at the case of the odd length array and the even length array that we have seen before, and you can notice that the sub problem reduces by 2 in size for every step. Now, what is the depth of the stack? You know that roughly n upon 2 calls will be done, because you start at a size n, the next call will be of size n minus 2, and so on until you hit either 1 or 0. So, you can work out that there will be about n upon 2 steps before you reach 1 or 0. The accurate expression is ceiling of the function, ceiling of the expression n upon 2 plus 1. So many calls will be there before you hit 1 or 0. So, each function call will take, let us say, constant amount of space, and there are about n upon 2 function calls. So, the stack depth is n upon 2, and therefore, the whole space, which is stack depth times the number of variables at each function, that will be about n upon 2. So, now let us consider a third example, which is computing the size, the maximum of a particular array. For concreteness, let us consider an integer array, and we have to compute the following function int max array. It takes two arguments, one is the array itself and the second is n, which is the number of elements in the array. Again, let us think about the problem recursively. We have written loops to solve the problem earlier, but now let us think about it in a recursive manner. If the array contains 0 elements, then what is the maximum? Okay. So, here it may be slightly counterintuitive if you are seeing this for the first time. The maximum of an empty array is some large negative value. Think of it as minus infinity. Why do we do this? This is because let us take maximum of, let us take a concrete example 1, 2, 3. Okay. We know that the maximum of this array is 3. Okay. Now, what happens when you take a larger array, array or list of numbers? So, what happens if you take, let us keep this unspecified, okay, A is an int. You know that if A is less than 3, then the maximum of this array is going to be 3. If A is greater than 3, then the maximum of this, the second one, is going to be greater than that. Okay. So, in any case, whatever be the nature of A, you can always say that maximum of 1, 2, 3 A is going to be greater than or equal to the maximum of 1, 2, 3. Now, what that means is that if you take a larger set, its maximum is always going to be greater than or equal to the maximum of a subset. Okay. This is note that this is independent of A, because you can analyze by cases. If A is less than or equal to 3, then this maximum will be 3 itself, and 3 is greater than or equal to 3. If A is greater than 3, then this maximum is strictly greater than the previous maximum. Okay. So, maximum is always monotone in according to the subset relation. Now, this means that what will be the maximum of the empty set? Okay. The empty set is a subset of every set, right. So, no matter which S I pick, maximum S has to be greater than or equal to maximum of the empty set. This means that a reasonable value for maximum of empty set is minus infinity. Okay. So, we set, so this is a reasonable convention. That is why when n is of size 0, we return some really large negative value, okay, by which I mean the absolute value of the number is really big, because we are trying to say that it is essentially minus infinity. If n is of size 1, then you just return A of 0, because the array contains only one element, its maximum will be A0. If n has size at least 2, okay, now we are in business, we have to solve the problem in terms of a subproblem. So, here was an example where the base case had to be really thought of, but now we are at the case where we are at thinking about the recursion. So, what is the recursive step here? Okay. So, let us take a concrete array. We have array A, which contains the numbers 2, 4, 3, 7, 5, 23, minus 3 and 9, some concrete array, and we want to say that I want to calculate the maximum of the array A in terms of some subproblem. The natural subproblem that we can think of is the subproblem of finding the maximum of this subarray, which starts from A1 and goes on until the last element. Okay. So, recursive call should be something like max array A plus 1, and there are n minus 1 elements in it, because we omit the first element. Now, maximum value, how can we solve the whole problem in terms of the subproblem? Suppose we know what is the maximum value in the tail, okay, A plus 1 to containing n minus 1 elements. The maximum of the whole array will be the greater of the two numbers. Which two numbers? The maximum of this subarray and A0. Okay. So, maximum value is the larger of A0 and the maximum of the tail subarray, which is A plus 1 to A plus n minus 1. Now, in order to compute the subproblem, we call a recursive call to the same function. It looks for the max array from A plus 1 containing n minus 1 elements. Okay. So, in this example, the maximum of the tail subarray will be 23, okay, and let us say that A0 is 25. So, the maximum of the whole array will be the greater of the two numbers 25 and 23. Okay. So, in this case, the maximum value will be 25, which is A0. So, now let us write this code. Okay. So, the recursive function is very simple, and this is one of the reasons why people like to write recursive functions, because from a recursive function it is very clear what the function is going to do. Usually recursive functions are shorter than their loop versions, and they are easier to understand when you read someone else's code. So, let us solve max array using a recursive function in C. We have int max array because it is finally going to return an int value, which is the greatest value in the array. Now, you have an int array A and n is the size of the array. Let us say that we set some max val, if n is 0, then the maximum is simply something like minus infinity. Let us keep it at a very large number, minus 99999, so minus 59, some large value, it does not matter. And then if n minus 1, if n is equal to 1, then the array contains only one element and therefore, it is the maximum. Okay, so, you just return A of 0. Otherwise, n is at least 2. So, in this case, you say that the maximum value of the sub problem is max array A plus 1 n minus 1. So, this is the maximum of the tail array. Now, once you have the maximum of the tail array, the maximum of the whole array is the greater of the two numbers, which is A0 and max val. Okay. So, we return max of A0 comma max val. Now, max is a function that is already there in the standard math library in C, but if you want to write it, it is not a difficult function to write. You can take two integers and return the greater of the two integers. Now, we can think about, is it better than the loop version of the program? The advantage of the recursive program is that it is easier and in some sense it contains fewer number of lines than the loop program. The more the disadvantage is that it takes up more space while executing. Okay. So, the questions are how much time does the function take, how much space does the function take, and there is also a, so these are things which are concrete and can be measured. There is also a softer question, which is how easy is it for a programmer to look at this function and understand what it does. In the second criterion, it is the recursive function that scores. In the first criterion, it is often the iterative function, the loop function that scores. So, please think about these questions, and you can work through it and say that in order to solve max array of an array of size n, let us take an array of size 8, you will see that these are the recursive calls it will make: a plus 1 7, a plus 2 6, so on up to a plus 7 1. And when you hit an array of size 1, you get to one of the base cases, which is that when you have an array which contains a single element, the maximum is the only element in the array. So, once you hit here, you will start returning. So, the maximum depth of function calls in this will be the size of the array. So, you can say that stack depth is n. Okay. Now, recursive programs are general programs, just like loop programs are general programs. You have written loops even before you saw what are arrays in C. Similarly, you can write recursive programs which deal with general data, not just array data. And in all of these questions, you can ask the question, you can ask the following questions: how much time does the function take and how much space does the function take? Okay. We will see an example for a recursive function that will read n numbers and returns their maximum. Before we came to know of C arrays, this is the kind of loop functions that we used to write. We would take n numbers. So, first you will read how many numbers to read, then you will read exactly those many numbers and find their maximum using a loop. Now, let us try to do that using recursion. We are not going to use any arrays. Okay. So, what we have to do is write a function read max. It takes n elements, and the logic is the same as finding the maximum of an array, but we will do it without using arrays. How do you do this? If you have 0 numbers to read, then you return minus infinity or some approximation, some large negative value. Otherwise, you read the first number. If n is equal to 1, that is we had to read only one number, then you just say that x is the maximum. Otherwise, n is greater than or equal to 2 and we have read one number. So, you say that return the maximum of the two values, which is x, okay. And what goes inside? Inside you have to solve a sub problem, which is the sub problem of reading n minus 1 numbers and returning their maximum. Go back and compare the program with finding the array maximum, and the recursion works exactly in the same way. So, we will read n minus 1 numbers and return the maximum of those, and then you compare maximum of the first number and the maximum of the sub problem. This is exactly as before, except that we did not use any arrays. And how do you call this function? You just declare a main function with n, you scanf how many numbers to read, and call the function read max n. Finally, it will return the maximum of the n numbers read, and you just print that value. Okay. So, think about this for a minute and see why we did not need to use arrays. Okay. Now, there are other functions which are typically written in a recursive manner. We just saw that you can use recursion with arrays. We saw problems where you do not need to use arrays, but you can still write a recursive routine. Now, we will come to arithmetic functions, and many arithmetic functions are often recursively defined. For example, let us take the GCD function, Euclid's algorithm, and you can write the GCD function as follows. You first ensure that A is greater than or equal to B using the swap function, and then you just call GCD of A comma B, and GCD of A comma B is defined recursively as follows. If B is 0, then GCD of A comma B is A. If B is non-zero, then you just return GCD of B comma A modulo B. Okay. So, this is how you write the recursive GCD routine, and I will make the claim that this routine is cleaner than the iterative routine. In the iterative routine, remember we had to use an intermediate variable which will store the value of, let us say, A, and then did a careful three-way exchange in order to accomplish B comma A modulo B. Here the code is very simple. If B is 0, then we know that GCD of A comma B is A. If B is non-zero, then we know that GCD of A comma B is GCD of B comma A modulo B. So, it is a very concise way of writing the function. Now, which you can ask the question, which is better, is it the recursive formulation or the iterative formulation? Logic is the same, so it will take the same number of steps. So, the time taken will roughly be the same. And we have also made the claim that the recursive version is easier to understand. The disadvantage may be the following, that the recursive function may use a very deep stack. Okay. So, you can ask a question like how deep will be the stack in the case of the recursive program. So, in the following video we will talk about more general kinds of recursion. In this video and the previous video, we have seen recursive problems which can be solved by one call to a sub problem, okay, and we will see more general kinds of recursion.